Welcome to the lab. I'll be your friendly tutor today for this explainer, as we demystify what I think is one of the most fascinating subjects in all of science, electrochemistry. Ever since the earliest scientists started playing around with conductive metals and these mysterious bubbling liquids, we've been trying to figure out how chemical bonds actually translate into the electricity that powers literally all our everyday devices. Today, we're going to break down that history and the sheer mechanics behind it. So grab your lab notebook, because we are about to map out the exact blueprint of how energy flows. Here's a quick look at our syllabus for today's session. We'll be moving logically right from the foundational definitions of the electron engine into the two core cell architectures, the voltage tug-of-war, decoding the math, and then finally looking at real-world commercial batteries and the broader electrochemical universe. All right, let's kick things off with part 1, the engine of electrons. If you are prepping for an upcoming chemistry test, you want to lock this concept in right now. In electrochemistry, it is all about the movement of electrons. Oxidation is the loss of electrons, and this process always, and I mean always, happens at the negative anode. Reduction, on the other hand, is the gain of electrons occurring at the positive cathode. Here is a classic tutor trick for you. Just remember an-ox and red cat. Anode is oxidation, reduction is cathode. Get that locked in your brain, and I promise the rest of this explainer will be an absolute breeze. When you step back and look at the big picture, you can kind of think of this like an invisible circuit. Over on the left, at the anode, chemical energy is actively pushing electrons out. They travel up and zip through a wire, which, by the way, is our actual flow of electricity, performing useful electrical work for us before they finally arrive at the cathode on the right, where they're consumed. It's just this beautiful, continuous cycle of chemical energy transforming right into electrical energy. Let's look at a really classic historical example, the Daniell cell. Early electricity pioneers realized that if you physically separate the oxidation of zinc from the reduction of copper, you can literally force those migrating electrons to travel through an external wire. But hey, notice that little U-shaped tube in the middle? The salt bridge. Listen, this is a massive exam point. Without that salt bridge allowing ions to flow back and forth to maintain electrical neutrality, one side would become way too positive and the other way too negative. Our little chemical engine would completely stall out in mere milliseconds. Moving right along to part 2, two core cell architectures. Okay, so every single concept in this field belongs to one of two opposing flows, and it's actually pretty wild how different they are. On the left, we've got a spontaneous reaction. This is producing electricity naturally, like a battery lighting up a bulb. The chemicals literally want to react. But on the right, you have the exact opposite, driving chemistry. This is where we pump external electrical energy, like from a wall outlet, into a beaker to force a totally non-spontaneous chemical transformation to happen. Think of plating a key with gold or silver. It is amazing that we can just reverse the natural flow of nature like that. When you're comparing these architectures, a great study guide trick is to look at them as total opposites. A galvanic cell converts chemical energy into electrical energy entirely naturally. But an electrolytic cell, it does the exact reverse. It uses electrical energy to force a chemical change. And here's the kicker. Because they are opposites, their charge signs flip too. So in a galvanic cell, the anode is negative, but in an electrolytic cell, the anode is actually positive. Definitely keep that in mind for your homework. Just imagine manipulating this system in real life. If you have a standard galvanic cell humming along, producing, say, 1.1 volts, and you apply an opposing external voltage that is exactly 1.1 volts, boom, you hit equilibrium. The engine halts entirely, no current flows. But if you crank up that external voltage even higher than 1.1 volts, you overpower the natural chemistry. You run the entire engine in reverse, totally turning your spontaneous galvanic cell into a forced electrolytic state. Let's dive into part 3, the voltage tug-of-war. So we keep talking about voltage, right? But here's a tricky problem early chemists ran into. You actually cannot measure the potential of a single half cell all by itself in isolation. You always need a pair to get a reading. So scientists brilliantly agreed on a universal benchmark, the standard hydrogen electrode, or SHE for short. They arbitrarily assigned it a potential of exactly 0.0 volts. Think of it kind of like sea level in geography. Every single other chemical reaction is measured by whether it sits above or below this electrical sea level. From that 0 point, standard electrode potentials reveal this massive elemental tug of war. If you look at this scale, you'll see fluorine sitting at the very top with a positive 2.87 volts. It is the ultimate electron thief. It pulls electrons the absolute hardest. Then, down at the very bottom, we have lithium at a negative 3.05 volts. Lithium is a highly aggressive reducing agent. It basically wants nothing more than to just shove its electrons away. And honestly, this is exactly why lithium is the champion material for those powerful batteries inside our smartphones and electric cars. All right, part 4, the math of electrochemistry. Let's decode this. Okay, take a deep breath. Please don't let the math scare you. I'm going to break down exactly what these intimidating formulas are actually telling us in plain old English. First up is the Nernst equation. So, while the standard voltages we just looked at assume pristine, perfect laboratory conditions, the real world is messy. As a battery runs, it consumes its chemical reactants, right? Well, the Nernst equation bridges thermodynamics and electrochemistry to calculate how a cell's actual, real-time voltage naturally drops as products build up and reactants get depleted over time. It's basically the mathematical proof of why your flashlight gets dimmer and dimmer as the batteries die. Now, what if we're the ones forcing the reaction? Let's say we want to find out exactly how much solid chemical product we get from a forced electrical input. Like maybe we want to electroplate solid silver onto a piece of jewelry. For that, we rely on Faraday's laws. Michael Faraday discovered this amazing rule. The amount of chemical reaction is perfectly proportional to the sheer quantity of electrical charge you pump through the solution. Honestly, the best way to think about this is treating it like a simple currency exchange at a bank. Step 1. Calculate your total input charge by multiplying your electrical current by the time it was running. Step 2. Convert that raw charge into our chemical currency, known as Faraday's, where 1 Faraday equals exactly 1 mole of electrons. And finally, step 3, just use the reaction standard stoichiometry to predict your physical output. 3 simple steps to literally convert invisible amps and seconds into actual grams of solid metal. Moving on to part 5, real-world commercial batteries. Let's step out of the theoretical lab for a second. Have you ever actually stopped to wonder about this? All the diagrams we've looked at today involve these big, open glass beakers full of sloshing, highly acidic liquids. So how on earth do engineers safely package these sloppy, wet chemical reactions for everyday consumer use without, completely ruining our electronics? Well, the answer lies in some seriously clever battery engineering. Commercial power sources are divided into 2 distinct classes, and it's based entirely on whether their internal chemistry can be reversed. Primary batteries are your single-use guys. Once the reactants are depleted, the battery's dead and it hits the recycling bin. Secondary batteries, on the other hand, are rechargeable. You can plug them right into the wall to force an external current backward through the system, completely resetting the chemical reactants. Let's look inside a primary cell, like the standard AA dry cell you'd pop into a wall clock. To solve that sloshing liquid problem, engineers brilliantly replaced liquid electrolytes with moist, thick chemical pastes. By wrapping a zinc container around a carbon rod and packing it full of this paste, they created a highly compact, totally leak-proof cylinder. It delivers a nice, steady voltage until the zinc is chemically consumed. Pretty smart, right? Secondary cells, however, require a completely different architecture. Take the big 12-volt lead storage battery sitting in your car. It relies on incredibly robust lead grids submerged in a literal bath of sulfuric acid. The key difference here is physical resilience. When you start your car, it acts as a spontaneous galvanic cell. But while you're driving down the highway, the car's alternator pumps electricity right back into it. It becomes an electrolytic cell, forcing solid sulfates back into solution. It is specially built to endure hundreds of these violent back-and-forth charging cycles. And finally, part 6, the electrochemical universe. Let's zoom way out. We've talked a ton about engineered devices today, but I want to show you how these principles govern the natural world outside the laboratory. This is actually one of my absolute favorite concepts to teach, because it completely changes how you look at the world. Even common corrosion, just simple rust, is an electrochemical process. It's really just nature's spontaneous attempt to return highly refined metals back to their stable, oxidized state. When a single drop of water lands on an iron surface, it creates a tiny, highly destructive microcell right there. The iron acts as an anode and oxidizes, while the outer edge of the water droplet acts as a cathode. Literally millions of microscopic batteries are forming and destroying metal all around us, every single day. Wow, okay, we have covered a lot of ground today, all the way from the very first spark of electron flow to the rust forming on a bicycle in the rain. Here is your final tutor's cheat sheet. Remember the golden rules. Spontaneous flow is galvanic. Forced flow is electrolytic. Anode is always oxidation. Cathode is always reduction. As we close out this explainer, I'm going to leave you with a thought. Now that you actually know the invisible blueprint of energy flow, what other silent electrochemical exchanges do you think are happening all around you, or even inside your own body right at this very moment? Keep questioning, keep learning, and I'll see you in the next session.